Hello, good evening. I am happy to welcome Professor Pradipkumar Keskar. He will be the next speaker in this symposium. Dr. Keskar is from Pune and alumni of SPPU, Savitribai Phule Pune University. Currently, he is working at BITS Pilani. He was head of the department also in the Department of Mathematics at BITS Pilani, and prior to that he has held visiting positions at Mumbai University, University of Pune as well as Purdue University. And most importantly, on this occasion I must mention that he is student of Professor Shreeram Abhyankar. He did his PhD with him, Algebraic geometry, with Professor Abhyankar at Purdue University. So I welcome him for this symposium. Just for my personal association, that he is my classmate for MSc classes. So I am very happy to welcome him on behalf of Bhaskaracharya Pratishthan. And it is also very nice that he will be now with us in Pune, and Bhaskaracharya Pratishthan. He will have more association with Pratishthan. And he will be in Pune because he is retiring soon in the next week. He is retiring next week, and so he has decided to stay in Pune. So there will be more occasions that he will visit Bhaskaracharya Pratishthan. So we take this opportunity to felicitate him on behalf of Bhaskaracharya Pratishthan and request Professor Katre to offer a gift, a shawl, whatever. Keskar.
On the occasion of your retirement, so that we are more helpful to the Pratishthan, and because they are seeing you today. Yes.
Okay, so now I request Keskar to deliver lecture. His topic is polynomial criteria for some combinatorial objects. Keskar.
Okay, so to start with, I'd like to thank the organizers for giving me this opportunity to talk here. In fact, it is quite an honor to talk on the occasion of Abhyankar's birthday symposium. And I also would like to commend organizers for conducting this year after year, I mean, yearly phenomenon. And I'm happy to participate in it this time. So, Abhyankar is my teacher. So I would like to just talk about him for just a minute. I mean, so or a minute or more. So basically, his philosophy towards mathematics is represented in this couplet, the first two lines of the poem that he wrote, which became quite famous. So he wrote this poem after the lecture by van der Waerden, the famous mathematician. I think in Nice ICM probably, but these are the couple of lines that encapsulates his philosophy. Polynomials and power series, may they forever rule the world. And basically the organizers here, I mean, are showing love and affection to him because he has done quite a bit to the mathematical culture of the city. And also, I mean, we are all beneficiaries of what he has been and what he had done here. So his philosophy was like this, and basically he would like to explain the things in the simplest, I mean, with least amount of jargon and in most concrete form, so whatever mathematics he has. So he has conceptualized algebra in three compartments, or sort of three wide, I mean, compartments, I mean, which may mix with each other also. But one of them is high school algebra, which he was proposing, and that high school algebra deals with these objects, polynomials and power series. So things like, I mean, addition, multiplication are normal operations, and several other manipulations like rearranging the terms, factorizing, etc. Then second type of algebra that he classified was called college algebra, which dealt with objects like rings, ideals, and so on. And the third type of algebra that he nomenclatured was university algebra, which deals with more abstract terms like categories and functors and so on. And he always proposed for this high school algebra, though he wrote a lot of literature in college algebra because that was the appropriate language for the presentation. So he was quite enthusiastic about explaining the things to uninitiated students, you might say, I mean beginning students. So his methodology in Pune was the following, that when he came to Pune, he used to announce the lectures for college students, and he used to pass the message through our teachers, college teachers. So for example, in SP College, where Professor Modak, Professor Udipikar, and Professor Katre also, though he was not there when I was actually undergrad student there. So we used to get a message about his classes, about his lectures. Then he used to give some formal lectures. Maybe audience may drop after some time, and then he would call all of them to his home, and then his informal sessions would begin. And his sessions, I mean, I'm sure, I mean, many of you know about it, but maybe some of you don't know. So his sessions were very free structured. They would last quite longer, I mean 2-3 hours. I mean, more time you spent, more you learned. Also, I mean, those were very free-flowing sort of things. It was not just purely compartmentalized as mathematics. I mean, he used to talk about, I mean, say mythology, or many of the anecdotes. And all of these used to be mixed in such a way that, I mean, they were interlinked also. So for him, all of them were the same, I mean, compartment. But anyway, so you learn to know that mathematics is a sort of a lifestyle rather than just a profession as such while staying with him. And so it's a way of living. I mean, so for him, I mean, he used to work, I mean, you might say, I mean, of course, many mathematicians work for 24 hours a day. I mean, so anyway, so coming to this motto, I mean, so my talk today, one might want to fit in this motto because there are these combinatorial objects called difference sets, and we would like to give a criterion for difference sets in terms of polynomials, identities, or some polynomial conditions. So basically, the combinatorial objects we are bringing to the realm of this polynomial world. So, okay, that's the title. Okay, so the basic object that we are dealing with is called a difference set, and that is a subset of a group. And that subset of a group satisfies certain combinatorial properties. So we start with a finite group G, identity element E, and the order of the group is V, and K is a number between 0 and V, integer, and lambda is another non-negative integer. So these are all required to define a difference set. So you have a subset of this G. Oh, what's happening here? Okay, so a subset D of G is called a Vk lambda difference set. So provided, so of course V is the order of the group, number of elements in the group. K is the size of this set, D has size K, and the extra combinatorial property that we require is this third quantity which comes, lambda plays the role there. So you look at ordered pairs R and S, both R and S coming from D, such that Rs inverse is equal to G. And how many such ordered pairs are there? That means in how many ways you can write G in the form Rs inverse, wherein Rs are coming from D. And this is for non-identity elements. So when G is additive, you can say this RS inverse is the difference. So you can say that every non-identity element of G can be written as difference of elements of D in lambda ways, and that's what this so such set G from which these R and S come, D, that's called a difference set. So it's a subset of G with these properties. So this V, K and lambda, these are called the parameters of this difference set D. And there are some more terminology. For example, order of D, that's the terminology that is this number K minus lambda. And this difference set is called planar if lambda is 1. That means every element, non-identity element can be written in unique way as difference of elements of G. So, and then we also use the terminology for D, like D is called abelian difference set in G, if G is abelian, or cyclic if G is cyclic. So actually the history began with cyclic difference sets, then abelian, and then ultimately it led to non-abelian also. So let's go back to what are the historical origins, how this idea came up. Very briefly, I am just sketching where the concepts come from without going into details. So first occurrence, or you might say, possibly first occurrence of difference sets occurred in the work of J. Singer. His work was related to finite projective spaces. And simultaneously almost, it came from other sources also. So this R.C. Bose, he was a statistician from Indian Statistical Institute, initially, later he went to US.
So this difference set is used to construct that balanced incomplete block design?
Right, yes. So, so this R.C. Bose, in fact, he was dealing with balanced, so these designs, and his designs occurred through statistical experiments, and certain designs can be related to this different concept of different sets. So R.C. Bose was another originator for this concept, and much later, much influential work for different sets came through the work of J.F. Dillon, who was a cryptologist. So his work was related to certain Boolean functions. So in cryptology, you encode the messages using sequences of zeros and ones as for digital communication. So certain type of Boolean functions. So those are so actually Boolean functions are maps from. So m variable Boolean function is map from f2 to the power m to f2, where f2 is a finite field with two elements, 0 and 1. So you can look at the support of this f. So these bent functions, their support of such Boolean functions which are different sets of a particular type, or rather, those are different sets in f2 to the power m, and their parameters have to be certain specific things. Let me not go into more details. Of course, this function would be balanced if there are half ones and half zeros, but these bent functions are not balanced. So slight deviation is there from, so for half of them, so you will require slight deviation from half of the size of this group. So let me not go into details of this, but that's how these work.
The range of f?
Range is f2 field with two elements. So, the value taken is 0 and 1 again. So, okay, so these are the various works through which this different sets came up. So applications of these different sets, one of the application is cryptography. For example, there are something called advanced encryption system, that is AES or DES. So these are some crypto systems, and they involve some substitution cipher. So one Boolean sequence is represented by some another, And in this substitution process, these bend functions occur. They are used as one of the components in this substitution cipher. I mean, so these are called S boxes. So those are part of these S boxes. So in cryptography, these bend functions occur, these different sets occur. They also occur in signal processing. So signal processing, our signals are again, either you can say those are sequences of zeros and ones, or multiplicatively you can say those are -1 and 1. If you look at the multiplicative group instead of additive group, then those are -1 and 1. So if you want low autocorrelation binary sequences, then their support also is, I mean, so different set gives rise, if the support is different set, then you get these sequences with low autocorrelations, and those are used in signal processing. And they're also used in graph theory to construct strongly regular graphs. So I'll not go into details of this concept of strongly regular graphs or graph theory as such. But this is the significance of this topic of different sets. So just to give one example before we go forward, I mean, so this is corresponds, this is given by Pele, Todd, and also Hadamard's name is associated with this. So suppose you consider additive group of finite field with q elements, and q is of course power of p, but you assume q is a number of the integer of the type 4m minus 1. So that means q is of course odd, but congruent to 3 mod 4. So if you have this group G, then you look at the squares of this field and take that as a, I mean, of course non-zero squares. So they take that as your D. And then it turns out that this D is a different set of this G with these parameters 4m minus 1, 2m minus 1, and m minus 1. That means every non-zero element of FQ, you can write it as difference of squares, non-zero squares, in exactly m minus 1 ways, where m minus 1 is lambda here. So this is one of the examples that occurred very early, say in the 40s. Anyway, so one can see this as an exercise. So one key here is that -1 is not a square. Because you can see that if -1 were a square, then there will be element of order 4 in the multiplicative group. But multiplicative group has order 4m minus 2, and 4m minus 2 is not divisible by 4. So that's one of the key things in proving this. And another key thing that you can see is that, okay, so you can look at, suppose x, you can write this as a square minus b square. Then if you multiply this x by c, or c square x square, this also you can write it as difference of squares. And so there is a one-to-one correspondence between representations of x as difference of squares and representations of cx as difference of squares. So if this can be written in certain number of ways as difference of squares, then c square x, sorry, that can also be written as difference of elements of square in same number of ways. And then you can also see that minus x, also you can write it as difference of squares, and exactly, I mean, you flip this paired AB. So these numbers and these, for minus x also it is the same thing. So you can see that every element of FQ is either a square or it is -1 multiplied by square, because -1 is not a square. So you can see that if x can be written as difference of two squares in certain number of ways, any other element y, non-zero element, you can obtain it by multiplying x by certain element of FQ. But certain element of FQ is either a square or minus of a square. So you can also see that that will have representation as difference of exactly same number of difference of squares representation. So using this idea, I mean, you can conclude that this D is a difference set and with these many parameters.
G is also a group, right?
G is the additive group, yes, I mean of the finite field. D is not necessarily a group. D is not a group.
Squares, huh?
It's just a subset.
No, our operation is plus. With additive operation, it is not a group.
But with the multiplicative structure,
Yes, but that's not a part of our operation of G. So I mean, with it is not a subgroup.
to start square is not a group.
No, that's perfectly all right.
I'm not objecting anything to what he's saying, but is D a group or not under multiplication?
No, D is group under multiplication, but it's not a subgroup of G.
Under multiplication, it's a group.
Yeah,
Under multiplication, it's a group, and
right.
probably that plays some role.
Yes, that's what I mean. There are two cosets as a part of multiplicative group, and -1 is the representation of another coset, and 1 is one of them.
Plays some role, but we may not highlight it.
Yeah.
He said that, that's exactly that. Yeah, that's exactly what he wrote on that board.
Okay, so this was one of the classical examples. I mean,
Different structures, the additive thing is elementary abelian group. That is.
right. In this case, yes, yeah. Okay, so now once you know some example, I mean, you might be wondering, I mean, what is there to learn? What is there to do in this different sets? So there are several questions which are still not answered. One of them is, suppose you are given these parameters Vk lambda, and G is given with order of G is equal to V, and K and lambda are given, and we ask the question whether there is a Vk lambda difference set, whether it exists inside G. So this existence of different sets in a given group with given parameters. So this is not a completely answered question. There are lots of open questions here. For example, even as small groups as I mean this Z3 cross Z9 square. So your G is this. So order of G is what is it? 81 into 3. I think that is 243. So your V is 243. So this is a group of size 243. So whether suppose we want to take lambda to be 60, and then it so happens that there is a relationship between K, lambda and V that is called riser identity. This riser identity is that K into K minus 1 is always V into lambda. So once you use this identity, you just need two parameters, and the third one is immediate from this. I mean, of course.
V minus 1 into lambda.
Oh, sorry. Thank you. Yeah, V minus 1 into lambda. Okay. So this riser identity, once you know this is your V, and you know lambda, of course, K, you can find out whatever K comes up. And is there Vk lambda difference set here? That is still an open question. So is so this is not known yet. So
Computers cannot do it.
yeah,
Computers cannot do it.
somehow yeah. I mean too large a number. Yeah, I mean still.
This Vk lambda difference set we have.
Yeah, there are too many cases to be checked. I mean, so Sunny will probably. I mean, no, so
It's an abelian group actually.
this is abelian element. This is not elementary. This is an abelian group. I mean, very small abelian group, but it's not known yet. So, I mean, and there are several cases where solution has been known. I mean, basically there is a person called Arasu who has settled several cases. Yeah, and several others also. And there are different techniques that have been employed, but still it is not known. Okay, yeah, sorry, I'm going back. Okay, so existence is a special case of this answer, this question. How many different sets are there for a given parameter? So if answer is 0, then you have answered the first question. But you may ask, if there exists, then how many? That can be asked. So because first question is not answered, second is also not answered. So then how to construct a different set with given parameters? So there are different constructions that are provided, but those are not, of course, exhaustive, and still new ways of constructing different sets would be advisable. Then the next problem is how to characterize. Suppose you are given already a subset of G. How do you decide whether it is a different set with given parameters or not? That is also some problem that is still not completely tackled. So there has been a lot of work, but it's not completely settled. So these are all open challenges still. So it's worthwhile. I mean, at least one feels that one could put some efforts into it, though a lot of effort has already been put. So yeah. So okay. So for example, this condition is a necessary condition. I mean, if it is a different set, then this condition is satisfied. That means if this condition is not satisfied, then it is not a different set, Vk lambda different set. But you want necessary as well as sufficient condition in some simpler format for to know whether something is a Vk lambda different set or not. Our work is about giving a polynomial criterion, and we require our different set to be abelian. So our work is that, I mean, for abelian different sets, we have been able to give a criterion which tells you that certain polynomial equations have to be satisfied, and whenever those are satisfied by certain object related to that set, and that is true if and only if those are different sets. So we gave a criterion for different set in terms of certain polynomial equations. And this is how, I mean, we come back to, I mean, polynomials and power series. So, I mean, of course, our assumption is that our different set is abelian. So, before going to this criterion, I mean, we must, I mean, give a nice representation. So, we are given a subset. So, T is a subset of G. So rather than considering this as a form of a subset of G, we would like to give a neater form for representing this subset, and that we call point representation. So what we do is, I mean, suppose G, elements of G, we list them in certain order. So this order of representation of elements of G is fixed. List is fixed. And then we consider the characteristic vector. So if T is any subset of G, we can consider a characteristic function of T in G, and that will give rise to this vector A1 up to AV. And these, of course, 1 and 0, we take them as complex numbers. And then you will get a n-tuple, or sorry, v-tuple of complex numbers. So we know that characteristic function determines the set, and set determines characteristic functions. So if we want to know T, then we would just know this vector of zeros and ones, and their support will give you T. So instead of vectors, set itself will consider this characteristic vector or this point representation. So now we can give algebraic criterion or polynomial criterion for which vectors in C, C to the power V are such type of vectors. So we know that, I mean, 0 or 1, every entry is 0 or 1, that means it has to satisfy this equation. A square is equal to A. Those are exactly the entries which will give you zeros and ones. So we have got a polynomial criterion for this. Of course, that's very trivial. But now, I mean, of course, we know that these tuples are finite if you require the entries to be zeros or 1. And the tuples which correspond to different sets is going to be still smaller set. So that is also a finite set. So if I consider these characteristics or point representations of those subsets which are different sets, that is still a finite set whose entries are zeros or 1, I mean tuples with entries zeros and 1. And so these are finitely many points in complex and v-dimensional space. And we already know that that's an algebraic set. And we know that there exist some equations f1 up to fr, so that their vanishing exactly gives this these points. So I mean, so if you already have a grasp over these equations, if you already know these equations, then you have got some criterion, because what happens is that, I mean, if you are given a subset of G, you look at its point representation and verify whether these equations are satisfied by that vector, and if they are satisfied, it's a different set, otherwise it is not. But here this is just an existential theorem that such f1 up to fr exists. So our problem is to exactly determine what are these f1 up to fr. And then many problems get solved. I mean, once we have this, of course, solved means, I mean, still there will be some tricky issues, but at least potentially they will be solved, because if we are given a subset, you want to check it is a vector, it is a different set, you just have to plug it inside these equations and see they are satisfied. Then further, if you want to count the number of different sets, you have to see how many solutions are there, common solutions are there for these equations. And if you want to construct the different set, then you have to construct the solutions. So once you have gotten hold of these equations, then everything is, I mean, many problems can be handled. But then still, I mean, there would be issues, because even if you know the point, I mean, you have to see whether the equation is satisfied. So that may not be easier identities. I mean, so there may be tricky identities you may have to use there. But potentially, this solves several problems, and this gives algebraic criterion for a subset of G to be a different set. So how to get hold of such equations, that is going to be an issue. So what we are going to do is, in case G is abelian, then we would give, I mean, these polynomials, though they are complicated looking, but we will give these polynomials. And before going to, I mean, so this is one step that you have to look at the characteristic vector for this T. That means you get a point of c to the power v, and then you are going to apply these algebraic techniques. Now, in case G is abelian, we can proceed further to determine these different sets, these polynomials. So before that, we must have some other criterion which we would like to transform into polynomial criterion. So this is called a group ring criterion. This is an age-old, I mean, I think since late 40s, at least this criterion exists. So, so this criterion, you have to consider this group ring of G. Group ring of G is just a, you can think of this as a finite combinations, additive combinations of, free combinations of elements of G. So you can write this as CG. This is CI, GI. I goes from 1 to V, where CI's are in complex numbers, and these are formal sums. And how do you multiply these things, and how do you add this? Adding is component wise, of course, and multiplication is the simplest way. You distribute and then collect the like terms together, and that gives the multiplication. Yeah?
Can you explain that why, I mean, my understanding of this necessary condition, I'm just going back slowly, like, so you have a K subset.
Yes.
And then K into K minus 1 differences, right?
No, it is a VK lambda difference set. Our terminology is parameters. There are these 3 parameters for these difference sets. VK lambda difference set. So this difference set depends on 3 parameters VK lambda. And then if there is such a difference set, these 3 parameters must be satisfying this condition.
Why is that's a requirement? Why this is a necessary condition? That's I'm trying to understand that. So you have a subset of size k,
Yeah.
and then you are computing, you are taking the order here, right? And then compute the difference.
Right.
And,
Yes.
And why this is v minus 1 into lambda? I mean lambda I understand.
V minus 1. V minus 1. Yeah.
So that's v minus 1 is because the non-zero elements.
That's correct.
Yes. Non-zero elements. Yeah.
Every non-zero element you want them to occur lambda.
Right. Yeah.
So this thing is by convolution, basically.
Uh-huh.
Anything you-
Right.
Those are finite number.
Yes. So that's a group ring, and so this is a certain ring with natural operations, and the criterion is to verify certain identity in this group ring. So if you have a subset T of G, this is one representation as point representation. You can also represent this T as, so suppose your point representation, this is point representation. You can also represent this as element of this CG, namely the sigma Ci Gi, and this is a way to represent this T inside this particular ring CG. So every subset you can represent it as a element of CG, and this is nothing but you can also write this simply as sigma G, as G belongs to T, because for elements of T, those are coefficients are 1, others elements are 0. So that's how you represent. So first of all, you represent subsets as elements of CG.
Group is now multiplicative.
Right, yes, group is multiplicative. So you represent it like this. I mean, these are formal combinations, so you don't combine these 2 different elements here. So once you do that, then and of course if T is a subset of G, you can denote T inverse to be every element of T is replaced by its inverse. Then you get T inverse, and then same thing written here, sigma T. I mean it's in this way, but you can also represent it like this. And then you have this theorem, which is one criterion for this subset to be a difference set, and that means D inverse. D inverse, of course, will be a collection of inverses of elements of D, and then this product is it's just element of xy. This is the product in the group, as x is in D and y is in D inverse. So that's what this D inverse means. Or you can say these are elements of the group rings. D, I can again represent it as element of a group ring by this, and then I am taking the. So I think I was wrong there. Sorry, this is not correct. So D, I am thinking of it as element of group ring like this, and then D inverse is another such sum, and I am taking the product. And this criterion says that this is differential dependently if this D inverse is lambda into G. G again is sigma Gi, where over all the elements, and in this identity element, its coefficient will be k minus lambda. So of course, you could write it this lambda E also you could absorb it. Sorry, okay, that's. Okay, if you forget E, for example, for the other elements it is easy to verify this criterion, because for a particular element you are seeing in how many ways, you can write it as element of D into D inverse as element here, and that's exactly K. So, sorry, that's exactly lambda. So, Anyway, so this is the criterion that deals with where D is this summation of Gi as Gi belongs to D. Similarly for D inverse, and then you have to verify similarly for G. So this is a criterion that gives you, so this is an identity of elements of CG, and that gives you the criterion. Now what we would like to do is we would like to convert this criterion into polynomial criterion, and all we have to do for this is we have to identify what is this CG. So this for abelian groups, we have the structure theorem for abelian groups. So that says that you can write it as direct product of cyclic groups, and using this particular structure theorem we can prove that group ring CG is nothing but this Cx1 up to xt, that is a polynomial ring modulo certain ideal, and this ideal is nothing but, obviously, I mean, you require that first component, I mean because it is coming from C1, its n1 power must be identity, and similarly for the tth component, nth power should be identity if it comes from this C and T. So this ideal is exactly, it happens to be the kernel of this particular, so CG is a quotient of this polynomial ring by this idea. And now what you will see is that whatever identity you want to prove in CG, you can write this as some element of CG equal to 0 in that form, and then when you go back to the other side, it will be some element on this in this quotient ring equal to 0. And what is the element of quotient ring, I mean equal to 0? All that means is that if you take the representative of that particular quotient ring, I mean that element must belong to I. So we are identifying this via this isomorphism. This group ring element is identified with this element and this coset, and then you will see that all you have to prove is that okay. So we get this group ring criterion is converted to ideal membership criterion. So what that criterion says is that so I consider this particular last line, that is, of course, I mean n1 power is going to be identity, so you can ignore that and you can write this as minus I1 power also, but because I want to make it polynomial, I have written as n1 minus I1 power. So this first one is a representation of D in the polynomial ring, second one is representation of D inverse in the polynomial ring, okay, and that is my D inverse, and the other side turns out to be, okay, let me see, okay, so where was I? Oh, I have to go forward. Sorry. Okay, so this group ring criterion we have considered. So for abelian difference sets, as we are saying, this structure we are using, and so this isomorphism we are using, and then we get this criterion is converted to the following criterion. Okay, so the first product, that is GD inverse, second product is element, I mean that corresponds to G, I mean because you are summing all the elements of G there, and then that has to be K minus lambda. So your criterion, I am representing these elements like this. So in this particular case I am looking at the generators, and G1 up to Gn are these generators of cyclic groups, and then this product of G1 to the power I1, Gn, Gt to the power It, its representative in the polynomial ring will be this, and it has to be multiplied by this characteristic vector term. So this is the criterion. So this, if you lift two polynomials, you have to say that this polynomial is in I. So the criterion reduces to okay, probably I. Okay, so my criterion is that this phi d, I mean this polynomial should be in the ideal I, and that ideal is just this particular ideal, x1 to the power n1 minus 1 xt to the power nt minus 1. I mean that's this ideal I, which we quotiented by. So, so basically we have to check whether a specific polynomial belongs to certain ideal. So that's the ideal membership problem. So now there is a lot of literature on this ideal membership problem that is discussed in computer algebra courses. For example, there is this book by Cox, Little and O'Shea, Varieties, Ideals and Algorithms. So it provides various ways of this, it gives you algorithms for ideal membership, and you can implement them using these softwares like Macaulay 2 or even Singular or even Sage. I mean those can be used to implement these problems, and they use Grosvenor basis of the ideals to verify this, I mean ideal membership. So you can convert this into this ideal membership problem, but now we would like to, so that's a sort of college algebra version in the language of Abhyankar, so because you are thinking about ideals. But if you want more explicit high school version, you might say, then you want to get exactly polynomial equations for this ideal membership. So of course some things we have to use, like there is this Hilbert-Nullstellensatz that we may want to use. So this ideal that we are considering is this x1 to the power n1 minus 1 up to xt to the power nt minus 1. So you look at all the points which are as common solutions of these equations, and so if a polynomial vanishes at all those points, then it belongs to radical of this ideal, that is Hilbert-Nullstellensatz. But this ideal you can see is a radical ideal. So in fact a polynomial will belong to this particular ideal exactly when it satisfies all the solutions, common solutions of that generating set. So and the generating set is, its common solutions are just t tuples zeta1 up to zeta t, where zeta is nth root of unity. So basically, I mean you have formulated this ideal membership. I mean you can also equivalently see that this polynomial will belong to this ideal exactly when in this, if you substitute this zeta1 up to zeta t, you should get 0. That will be necessary as well as sufficient condition. And that, so I mean when we are thinking like this, our variables are x1 up to xt, and then we may think of this given difference set, that means this point representation is fixed. But we want to revert the role now, and we want to vary this point representations. In that particular case, we want to give a condition on ci1 up to it, so that this condition is satisfied. And that idea is somewhat analogous to interpolation, because what this interpolation says is that if you are given a polynomial and you know values at finitely many points, then if you want to find this a0 up to n, all you do is you set up the equations in a0 up to n by substituting those values and getting those that particular value. So that gives you a system of equations in a0 up to an. So anyway, I mean, so we are now interested in these coefficients, because to identify a difference set is identifying these coefficients here, ci1 up to in, and we know which equations are satisfied, because if you substitute tuples zeta1 up to zeta t, then those will satisfy this phi d x1 up to xt will satisfy those equations. So if you plug them and set the equations in C, then you will get the equations for this point set, point representation of the different set. So, okay, so before going to that, I mean, if we are dealing with arbitrary elements of C to the power V, first of all, we have to know that it is a representation of some set. That means this second type of equations also we require. Second type of equations, that is after the union, that tells you that it is point representation of some set, and that set is different set. If you want to check that, then you have to see that if you substitute this zeta, where zeta is this tuple, zeta 1 up to zeta t, where zeta is the nth root of unity. So that has to be satisfied. So our polynomial criterion looks like this, that so if you are interested in a subset of D, I mean, in fact, you can beyond subset of T, you can start with any n tuple, and it will give you subset if these equations Ci square minus Ci equal to 0 are satisfied. Then it will be representation of some set, and if furthermore you have to satisfy some more equations, that is this phi of C comma psi equal to 0. If those equations are also satisfied, then you know it is a different set. So, that gives you the set of equations which you need to satisfy by this C1 up to, I mean, this point representation C. I mean, so there are two sets of equations. First set, there are as many as these zetas, and these zetas are exactly as many as elements of V, because those are n1 up to nt, and n1 up to nt is the size of G also, because C1 has size n1, Ct has size nt. So there are V equations.
If the group is of a prime power order,
Yes, yeah.
are the answers simpler?
No, not quite, not quite.
If the group is of order prime E,
Huh.
are the answers known?
Still, I mean, there will be several equations, because I mean, zeta has to vary over all the roots. I mean, not just primitive root. I mean, so you will still get several equations. I mean, some of them you can eliminate by taking just the primitive, I mean, primitive roots. I mean, that way you can reduce the number of equations, but still, number of equations could, I mean, still it will be a complicated problem.
Even for CP, it's a complication.
Yeah?
Even for CP, the group is CP.
CP, it will be easy, because CP, I mean, you, in fact, I mean, you can also see that sort of CP would be, because I mean, different roots differ by automorphism of G. So if one equation is satisfied for one zeta, then it will automatically be satisfied by the other. So that will reduce, first set of equations is reduced, but the second one you don't have any way to reduce. That means those are sequences of zeros and ones you still have to satisfy.
Some primes may be known for which there is a different sets in the set of CP.
In fact, for cyclic groups also, Sane, you are having some idea of, I mean, what are different sets of cyclic groups, etc. Most things are not.
CP, the answers are known.
There are some values of VK lambda for which there is no difference set.
There are. Of course, this riser condition has to be satisfied.
So riser condition is satisfied and still there are more.
Yes, but then, of course, I mean, what we are going to say is that whatever conditions you get here, I mean, so we get certain equations in this manner. So in fact, those are 2 into V equations, because V equations of first type for the order of the group, and V equations of the second type. So there are 2 V equations. Yeah, you are saying something?
No, he is saying, are there any other conditions? That is the Brackerizer-Chola conditions.
Okay. Yeah, but even, I mean, our equations is also a condition. I mean, so what we are going to get. So, and that also, but those are complicated equations. I mean, so.
Where, I mean, mean, somewhere these given equations were useful. Is there any such incidents where it is to be used?
Yes.
Because
Okay, so
Thing like, can you know can the multiplier thing be converted into this term? Or as a
I'm not quite.
Bellon theorem.
Ha, 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 ha.
Even if you have a different set, whether something is a multiplier or not is a difficult question. It's quite a hard question.
No, I have not thought about it. I mean,
Yeah, I mean you can actually, you can probably put it in this language.
Okay, yeah.
It will at least give an alternative setup.
Right, right, right. Yeah.
I'm not saying it will solve the problem.
So basically, I mean, we have been trying to give some applications to bent functions, but there, I mean, we have been able to say something is not bent using this criterion. I mean, so bent functions are used in cryptography as those were discovered by, used in these AES and DES setup for this encoding. So we have been able to say something is not a different set, but we have not been able to actually conclude something is a different set using this criterion. Okay, so but of course the setup says that it looks promising if you believe this Grosvenor basis people, because once there are algorithms for doing this, and algorithms possibly can be implemented using this software. So there are several conjectures about different sets which you can give a formulation. So one of them is a prime power conjecture. That conjecture says that a non-trivial planar abelian difference set of order k minus lambda exists if and only if k minus lambda is p to the power l for some prime p and positive integer l. This conjecture is open if k minus lambda is bigger than 2 multiplied by 10 to the power 10. So you can reformulate it using this language of, so basically you can see that difference set does not exist amounts to saying that okay, let me see if I have so basically what you are saying is that this tuple C1 up to Ct does not exist, or C1 up to Cv does not exist. That means these solutions don't have these equations don't have a common solution. And Hilbert-Nelsted again says that that just means that one belongs to the ideal generated by these particular equations. So non-existence of a different set just can be reduced to saying that one belongs to the ideal of these particular equations. So so this prime power conjecture, what it says is that there is no different set. It gives a criterion for existence of different set. So you can also convert it. Problem of existence is like whether one belongs to the ideal of these equations or not, and then you can reformulate it that this so J is that ideal generated by that system, and then so you have to, non-trivial means some trivial cases you have to deal out, so those are remove. So there are these values if you remove, then and for planar means lambda is 1. So if you put lambda is equal to 1, then this condition can be transformed. So one side that this different set does not exist just means one belongs to I, and the other side is of course can be formulated like this. So prime power conjecture can be reformulated in this language. Then there are several other conjectures which can be formulated. So one of the important conjectures is called Lander's conjecture for different sets. The Lander's conjecture, okay. So that's in the first paragraph. So D is a non-trivial different set of an abelian group G, and if P is a prime divisor of V and K minus lambda, so if this non-trivial different set exists, then Silo P subgroup of G is not cyclic. Okay. So again G is abelian here. So we can assume the decomposition of G, and if you have a decomposition of G as product C1 cross C2 cross CT, how do you characterize this that CLOP subgroup of G is not cyclic? In fact, that you can characterize by the fact that this prime number P, so this, okay, so this cyclic group is of course C1 N1 cross C2 N2 cross CT NT. So N1 up to NT, those are orders of the cyclic group whose product gives you G. So one condition that okay, I mean so this non-trivial part, that means you have to delete this last line. I mean these options of k and lambda have to be deleted, and then suppose we also assume P is a divisor of n minus k, that means this condition is also V and n minus k, that condition is also satisfied. Then you want to see that this difference set, I mean, okay, let me see. Sorry. Okay, so why am I saying lambda is k minus 1, k into k minus 1 divided by v minus 1? That is because of this riser identity. But you can also prove this as one of the equations. This is one of the equations that we have given. So for example, when we are substituting this, anyway, I mean we are substituting this various zetas. I mean, so if I take this zeta to be all, I mean roots of unity to be 1, then what equation do I get? That equation is exactly nothing but this condition. So this condition is also part one equation that we have, and further equations you can get by okay, let me see, where was I? I mean, I was okay. So these are some other reformulations. I mean, that's where we were up to. So this Lander's conjecture. I mean, so we are interested in when is so suppose G is a product of cyclic groups. When can we say that that's next slide. CLOP subgroup of G is not cyclic. In fact, whatever power of P, it suppose there are two different components Ci and Cj which have a power of P as a divisor. Then in the product, I mean, you will have a non-cyclic group of order P, order power of P, right? I mean, if some part is there in C1 also and some part is there in C2 also, then you can see that in the product there will be, I mean, product subgroup, I mean, some part inside C1 and part inside C2. If you take the product subgroup, that will be a P group, but that will not be cyclic. So saying, I mean, if P divides 2 of the ni's, then you are not going to get a cyclic, I mean, then there will be a CLOP subgroup which is not cyclic. Okay. So this condition that CLOP subgroup is not cyclic, that can be written in terms of certain divisibility property for these VI's. I mean, P does not divide 2 of the ni's. And if P divides only 1 of the ni, then CLOP subgroup will be part of that cyclic subgroup, and then it will be cyclic. So you have a necessary and sufficient condition for this CLOP subgroup to be not cyclic in terms of this N1 up to Nt. So, so that condition can be just numerically expressed, and then what you have to see is that the criterion just becomes, so first of course this one of the conditions when all the Ci's are 1, you will get this condition, the riser condition, that will be satisfied. So you can write for lambda this k minus 1 by v minus 1, and So what it will tell you ultimately is that if so we are going into looking at the contrapositive, that means for this Landau's conjecture. So if G is not cyclic, so if G is a Silopi subgroup of G is cyclic, then there does not exist a difference set, non-trivial difference set. So that condition will just, I mean, does not exist means just 1 belongs to J. And I mean, this divisibility property, I mean, there is no cyclic Silopi subgroup that can be expressed in the form that this V is product of Ni's, of course, and there exists a prime number P which divides Ni for exactly one integer I. That would just ensure that Silopi subgroup is cyclic, and then you can say that the difference set does not exist. That means that is equivalent to saying 1 belongs to J. So this is just under certain numerical condition, you reduce it to ideal membership problem. So okay, so I mean, do I have more time or? Okay, so I guess I'll stop here.
I think Professor Abhyankar has no connection with different sets, no? I think reading work.
In fact, he used, I mean, in our joint paper, we used something called Singer cycle theorem. And Singer cycle theorem is related to Singer's work on different sets. So, I mean, basically, that was one of the motivations for me to turn into different sets as such. But, I mean, of course, he didn't explicitly work with different sets or designs or, I mean, things like that. I mean, so he just used a very specific part of this consequence of different sets.
Yeah, in number theory also we have found out, I mean, cyclotomic numbers, do they form a different set or not? But
Okay,
the
yeah.
answer is negative. Many times you don't get,
Most of the time.
most of the, yeah, you don't get different sets.
In fact, I mean, the lot of work in characterization of different sets reduce those problems. They use representations of G, and then ultimately they convert it to certain algebraic number theoretic problems. So, I mean, proving certain ideal, I mean, again, I mean, that's a factorization of certain, I mean, ideals. I mean, so.
So, I mean, this idea is very interesting that you are converting to this into problems about rings. And
Polynomials, explicitly, yeah.
To say polynomial rings.
Yes, yeah.
Hilbert Lewis has also you are using, so that was not, I think, understood earlier. Such a criterion, I think.
Right.
I had not thought about that. So thank you very much for this nice talk.